part 2 of our talk about the first derivative test, we are going to look at two things. We're going to look at graphs and we're going to look at applications. So let's start with the graph. I have f of x is x squared plus 3x. We're going to start the same way we've been doing everything. We're going to take the derivative. So f prime of x will be 2x plus 3. And then we're going to graph that. Well, 2x plus 3 isn't too bad. It's just a line. So we go up 1, 2, 3. And then we have a slope 2 over 1. I could go the other way just so we have more than one point and we can graph it. All right, so here's the graph of the derivative. Now notice how different the graph of the derivative looks compared to what you would want the function to look like. So the function is x squared. We know it looks like a u, but the derivative is a line. What we're going to start looking at in the line is sometimes the line is below the x-axis. So here's the x-axis, and I have this time that it's below. And then I have some times that it's above, and I have a place where it happens to cross the x-axis. So what would this say? This is where the derivative would be 0. So that would be our critical point. What is happening? So the derivative was below the x-axis, which means it was negative, and then it switched to positive. So it was decreasing and it increased. That says this critical point that we found right here, that would be the minimum of the quadratic. So that's our shift in how we're thinking, is we start thinking, what does the derivative tell us? So let's look at some more graphs. This time I gave you the graph of the derivative, and we want to find the critical numbers, the increasing, decreasing intervals of the function. So we're going to take the derivative and figure out some things about the function. So we're starting with the critical numbers. Critical numbers is where is the derivative equal to 0. So that works like our x-intercept. So I have two of them. I have the critical numbers. When x equals -3 and when x equals 2. Okay, what do the critical numbers do? It shows me where the function changes from increasing to decreasing or decreasing to increasing. Well, when I look at the graph, it started off below the x-axis, so it was negative. That means it was decreasing. And then it pops up and it's positive for a while, so that means it'll be increasing. And then it goes back down under the x-axis, so that's negative and that's decreasing again. So what do I know? From negative infinity until it gets to -3, this function was decreasing. Then from -3 over to 2, it was increasing, and then from 2 to infinity, it was decreasing again. Let's put that together with some application. So this first one says the graph of the total revenue function, R of x in dollars, from the sale of x cordless electric screwdrivers is shown in the figure. On what interval is the marginal revenue positive? Okay. So this is the R of x. We don't have the derivative this time, but we're asking questions about the derivative. So it says, on what intervals is the marginal revenue positive? So marginal revenue, R prime of x, we want to know when would it be positive? Well, it's wherever the function is increasing. So our marginal revenue will be positive on 0 to 500. Then it says, on what interval is the marginal revenue negative? Well, the marginal revenue will be negative wherever the function decreases. So it decreases from 500 to 1,000. So we write from 500 to 1,000. Then it says, at what point is the marginal revenue 0? The marginal revenue is 0 where it changes. So this is my critical point. It was a maximum of this case, but this is where x is 500. Lastly, we're going to sketch the marginal revenue. Now notice the word sketch. That means it's not going to be perfect. It's just going to be kind of an idea of what it looks like. Important things I'm going to do to start is I'm going to put 500 there. Also 1,000, because our domain was 0 to 1,000. And then we said that the marginal revenue was 0 at 500, so 500 will be my critical point. We said that the marginal revenue was positive before, so we're going to make it above, and then it'll be negative until it gets to 1,000. So this way, we have a sketch. It was R prime of x is positive, our R prime of x was negative, and then our R prime of x was 0. The next one says the graph approximates the rate of change of the price of eggs over a 70-month period where E of t is the price of a dozen eggs in dollars and t is the time in months. Notice that the graph at the top, I don't know how well you can see it, that is E prime. So it says the graph approximates the rate of change, which means the graph is the derivative. We're starting with find the increasing, decreasing intervals. Right. So where does it start? It starts at 0, and at 10 you see it changes. It's 10, it's at 0. So for this part, from 0 to 10, this was below the x-axis, so this was decreasing. Then from 10 to 50, it was above the x-axis, which is positive, which means the price was increasing. And then again from 50 until 70, it was below the x-axis, so it's decreasing. So this says what's happening to the price of eggs. The price of eggs was going down for the first 10 months. Then it went up from month 10 to month 50, and then month 50 to month 70, it went down. So this was a down, up, down. Right. Find the local max and local min of the function. So what do we think about? We think about it was negative and it switched to positive. Negative, positive, this is a min. Where did that happen? At 10. So we had a local min when x equals 10. Remember, that was time. And then it was positive to negative, so up and then down. There's a max, and that's at 50. So we have a local max when x equals 50. Again, we're asked to sketch, and we're sketching the graph of E of t. I want to start by having the right domain. So I had a domain that went to 70. We had important numbers in there at 10 and 50, so I put in 10, 50, and 70 just to have some kind of gauge of what this looks like. All right, what did we say happened? We said we had a local min at 10, so let's just pick a place for it to be at 10 to say maybe it started higher and it came down to 10. It hit to 10 and it went up, so we want to make a max at 50. And then we want to make it go down. Now, it doesn't have to go to 0. I think sometimes we think, oh, we have to hit the x-axis again. But most of the time we're not getting x for free, so I don't want to put it at 0 because that doesn't seem very realistic. But it does show me it decreased, it increased, it decreased, I had a min, I had a max. The last one we have is a manufacturer incurs the following costs in producing X rain jackets in a day for X between 0 and 200. There are fixed costs of $450. Unit production cost of $30 per jacket, equipment maintenance and repairs, that's 0.08 x squared dollars. A says, what is the average cost C bar of X per jacket if X jackets are produced in a day? Then B says, find the critical numbers of C bar of X, the intervals over which the average cost per jacket is decreasing, the intervals over which the average cost per jacket is increasing, and the local extrema, and we don't have to graph this time. First thing we need to do to be able to find the average cost is start with the cost. So our cost function, it said we had 0.08 x squared for equipment, then a unit production cost of $30 each, and then we had fixed cost of $450. So here's our start is the cost function. To get average cost, we just want to divide that by x. Now, I would like to avoid having to do the quotient rule, so I'm going to reduce that. 0.08 x squared divided by x is 0.08x. 30x over x is 30, and then the 450, I'm going to write 450x to the negative 1. Part B asks us to find the critical numbers of the average cost function. So we are going to take the derivative. 0.08x gives us 0.08. 30 is a constant, so the derivative is 0. The 450x to the negative 1, the negative 1 comes down. We have 450x to the negative 2. To get the critical numbers, we need to set this equal to 0. So 0.08 minus 450x to the negative 2 equals 0. Says 0.08 equals 450, and I'm going to write this over x squared. So the 450x to the negative 2 moved to the right, and I changed it back to a fraction. I'm going to bring the x squared over with the 0.08, so I have 0.08x squared is 450. Then I'm going to divide by 0.08 and get x squared equals 5,625. Take the square root, take the square root. I get x is 75. Now, a lot of times we talk about when we take the square root, we say plus or minus. But here we're making jackets, and I can't make negative jackets, so I only need to keep the 75. I have one critical number. Okay. That was the first part. So first it says, find the critical numbers. So we found the only critical number, it was 75. Now we want to find the intervals where the average cost per jacket is decreasing and the intervals where the average cost per jacket is increasing. This will help us find the extrema. So we're going to use the first derivative test to break up the domain. Now go back and look at the domain was given at the beginning as 0 to 200. So we don't have this infinity to infinity part here. This time we have 0, we have the critical number of 75, and then we have the empty domain of 200. So this makes our interval 0 to 75, and then 75 to 200. We're plugging this into our marginal average cost, which was 0.08 minus 450. I'm going to write it over x squared. I think that'll be easier. So let's say we need to pick a number from 0 to 75. 1 looks pretty good. 75 to 200, I like 100. Okay. So I think about if I put 0.08 minus 450 over 1 squared, so I can even write it minus 450 over 1. 0.08 minus 450, that's negative, so I know right here this is decreasing. Let me move that up a little. Same thing with 100. I do 0.08 minus 450 over 100 squared. And it might make you feel better to put that in your calculator. I'll tell you, I got 0.035, but 0.035, most importantly, is positive. Positive says increasing. So from 0 to 75, this was decreasing, and that means my average cost was decreasing, and then from 75 to 200, my average cost was increasing. Decreasing and then increasing says that we have a minimum, so our only extrema this time is a minimum, so we have a local min when x equals 75, which means 75 jackets makes the average cost the smallest that it's going to be.